Okay, thank you for the introduction. How many sins can a man commit in a lifetime? I had a couple of dilemmas while getting ready for this presentation. One was the microphone. This, of course, is very handy because it enables you to walk around. At the same time, it gives a sort of a Britney Spears feeling, which is not exactly what I was looking for. And the other one, of course, nails you down to that place. That's always very hard to nail me down in one place while doing a presentation. So I choose for this one. And the other one, yes, was, well, which slide format should I choose? Should I choose Eindhoven or Delft? But my guess was that you would like to have an external guest speaker here today, so I thought, okay, let's take Delft. Besides that, I'm there 4 days a week, 1 day a week, only here now. So, but I'm indeed still one of us here. That's right. Yes. Right. Okay. I apologize for the typo in the title slide. Anyway, it's engineering, of course, not engineering. I apologize for that. What am I going to do? Well, that's very much in the title. I will try to argue that if educational research is looking for a role model, another science that would give some inspiration as to how to conduct research, that for a long time, and even still today, educational sciences, like many other sciences, have looked in the direction of natural sciences. They were seen as sort of the sciences. The sciences with the best predictability, the reliability was always fine, there was repeatability of the phenomena, so it was really like to see science to be done. And what I would like to do today is show you that perhaps natural sciences are not the best role model for educational sciences. In spite of the fact that still a lot of educational studies that I see today are indeed modeled after natural sciences. Now, in a while I'll tell you about the characteristics of natural sciences, the characteristics of engineering sciences, put them next to each other, and then suggest that the engineering sciences are not so bad and not the role model for educational sciences. So this is an inspiration day, so why do I do this? Who am I trying to inspire? Well, I guess a lot of you are just involved in teaching. Science, engineering educators, you're doing a daily job as a teacher, you probably do all sorts of things, lecturing and supervising experiments. And what I would like to reach, if I can, in this hour is inspire you to become at least more active users of educational research. But that would be the minimum. If that would be the end result, then I feel somewhat happy, but I think it would be even much nicer if you would be active participants in educational research. If you would not just let this educational researcher drop in and say, well, can I observe you and your students? But if you would say, I would like to have another role for myself. I would like to have a say in your problem statements. I would like to have a say in your data collection. I would like to have a say in blah, blah, blah. Even up to the end, like, I would like to have a say in where you publish the outcomes. So that would be nice, if that could be the result. So that's what I'd like to do as an inspiration for the educators among us. Now I know that there's also educational researchers, and for those, that message has to do with the role model that we're looking for. So I'd really like to inspire you to seek to make the gap between research and practice smaller, as small as possible. Well, that's of course something like an optimization problem. That's probably hard to do anyway. And if you can make it smaller, that would be good. And if you can, the next time, make it again a bit smaller, that's fine. Let me take away some possible misunderstandings first, because I'm going to say, maybe it looks like I'm going to say nasty things about natural science, but that's certainly not my intention. I do appreciate the role of natural sciences. I was educated as a physicist myself, so who am I to say anything bad about natural sciences? They have their value, absolutely. It's just that I want to suggest that they are not the only, and perhaps not even the best role model for educational studies. So, natural sciences, we all know, are very highly regarded, and even for the people involved in it themselves, it is sometimes so high that they can hardly understand what's going on here. The text down here reads, frankly, I even find it hard to believe some of the things that I've been coming up with. So that's natural science. It's always very deep and things that okay. But is it always usable? That's the point. Another possible misunderstanding What I certainly do not want to suggest is that education is something that can be engineered. That is like a machine with buttons on it that you can push or you can turn. And this may seem like not real what's going on here in this cartoon, and of course it isn't. But in some cases it is. And I can illustrate that by this slide, which comes from a recent Dutch report on quality of education. And it really takes an engineering approach. It really suggests that things like number of diplomas per year, study duration for an average student is something that you can regulate by turning some buttons, by pushing some buttons, and you can put then a target value and you can say, well, the target value of the average duration of a study for a student, a master student, will be like 4.5 years, something like that. As if that is something that you can just control, like you could control the machine. Well, you're engineers enough to know that even for a machine that is often difficult. And then it's only nuts and bolts turning around. But in this case, it's students who are much more difficult to monitor, if at all that would be the way you'd like to treat it. So that is something I really do not want to suggest. So when I suggest engineering sciences as a role model for educational studies, that is certainly not to say that education itself is something that is engineerable. So what then do I plead for? As I said, regarding educational sciences as a science that aims at improving education and not just describing it. And in fact, this is already one of the main points that I want to make, that the main goal of natural sciences is to describe, period. The natural scientist does not have an opinion about the electrons observing. While I think in educational sciences we should have an opinion on what we're observing. And there's still lots and lots of studies that just look at all sorts of interesting correlations between variables without even any kind of remark like, yes, this is what we would like it to be, or this is a situation that definitely leads improvement. A lot of these studies just end by saying, well, we found something very interesting, psychologically it's very interesting because this is apparently how our human mind works, but we just describe it from distance and without any value judgment. And that's, I think, what lacks in natural science. That's good for natural sciences. I'll show you that in natural sciences it's not even good to do that. But for educational scientists, we need more like the engineering approach, where we do have a value about the reality. So, what we're talking about, not natural science, but not engineering science, we're talking about educational sciences. Our object of study is education. And, well, the first question could be then, what is that? Is it, so it's not something engineerable, it's not something that you'd only like to describe. What is it? Well, I've been looking a bit for definitions, and recently I talked to Frank Schouten, who used to be the rector of the Free University until recently, and he said, I found an interesting definition of education. So I'm going to show you that. It's in German, I have to warn you, so be prepared. But for those of you who are Dutch-speaking, you will probably understand it, and for those of you who are English-speaking, maybe it's not so easy to grasp what's going on here. So what is education then, according to this definition? Wenn alles schläft und einer spricht, den Zustand nennt man Unterricht. Now let's admit that education for a long time was like this. You all know these pictures of rooms full of students that are sitting on their bench, bent over their table and apparently sleeping. Now, fortunately, we are here in engineering education, and there the situation is often, not always, but often different. We all, if we have sort of intuitive image of engineering education, we would rather see students tinkering on things and not primarily sitting in lecture rooms, especially with the new bachelor college that we have here, thanks to the inspiring leadership of Lex. Education really looks different now. So this is not anymore what it is. But for a long time it used to be like this, and to some extent it still is. But okay, this is certainly not what we want. Education is something very, very active. We would like it to be, at least, where students really are involved in doing active learning and not just sitting and listening. Some of the problems with educational studies then, and perhaps because they were based on this image of education, sometimes I worry about the outcome of educational research if at all the outcome matters at all? Does it have any kind of implication? Or is it like here when the prof says that along with antimatter and dark matter we've discovered the existence of doesn't matter, which appears to have no effect on the universe whatsoever. And even if in educational studies there is an outcome that may have implications for the universe, it is often not suggested or phrased by the researcher. So if there is it does matter, then we are not really informed about how it could matter. That's one problem. So does the outcome really give us a clue of how to improve education? Sometimes my impression is that we're looking for the obvious just because we want to make sure, or just because we think it is interesting theoretically, and so we're investigating the big banana, which appears to be a big banana, but we want to make sure, so we take a sample of 10,000 big bananas and we all give them a questionnaire and we throw it on the SPSS, and in the end the outcome is yes, this is a big banana. And that also worries me a bit. There's lots of studies like relations between motivation and attitude, and then the two appear to be correlated. Not a real big surprise, I would say. And then there are other studies that show that motivation is related to the success of the study. Not so revolutionary either, I would say. But still, these studies are done, and they take thousands of students and a lot of statistics to prove watertight that indeed there is this correlation. And my doubt is if this really makes a difference. Correlation is perhaps not even so interesting at all, but anyway. What also is seen by important for many educational researchers is to have complete control over the variables. That means that you're looking for experimental settings that are always a bit unnatural, because the real situation is always a bit fuzzy, always a bit chaotic, always difficult to control. So everything becomes a bit more difficult methodologically then. Statistics don't work anymore, and you have to change more than one variable at the same time, and sometimes you even have no complete control over your variable because you're really standing with 2 feet in the mud and you're trying to improve things without real control over all the variables. And a lot of educational scientists say, well, that's not what we want. So you want to create artificial situations where we do have complete control over the variables. And those give the nice statistics, and those give the good reliability, and those give everything that the journals want to see. I have to admit that the journals are largely cause of all these problems because they require such things. If you submit an article at one educational research and you sin against this kind of things, then you're quickly going to find out that you'll have trouble getting your stuff published. Not in my journal, of course, but in the other journals. And then there is the communication issue. Even if researchers have found something that might be of use, then they publish it in a journal that is usually not read by educators but by colleague researchers, and it is all phrased in such a way that only the researchers can understand it because the others are just flabbergasted by all the statistics and all the jargon that is used, etc. So in the end there is also a communication problem there. Now, I realise that this is all sweeping statements, and it's certainly not about all educational studies. There's a lot of good stuff out there, but I see a lot of educational studies that still suffer from, well, is it a problem? No, not if you're only interested in describing, but if you're looking for something that is applicable, something that you can use for practice, then it is a problem. And I think educational scientists should see that as a problem and should somehow make a shift in their minds about what to do with it. Also, the criteria that we're using. I mean, if you use precision and significance, that can be quite different things, of course. I mean, a lot of educational studies look for particularly statistical precision. You want your reliability coefficients to be as high as possible. If you look for significance, the sort of messages that you want to pass on is perhaps a bit different also. So there's also an issue there. What kind of criteria do you use in the research? When are you seeing your study as a valuable study? This issue of criteria is interesting because there has, in 2011, been issued a report by the KNAW about quality assessment in designing and constructing disciplines, just to give you the opposite. And this was for educational studies. Now we're moving to engineering studies, because that's what it particularly was meant for. And they mentioned, yes, sure, scientific criteria, no doubt about that. Yes, you have to have your publications, and you have to have your designs also, but they have to not be just designs, but also with some sort of scientific account behind them. But explicitly mention also as criteria for engineering research that there is external use. And you probably all know that if you want to submit an STW application, you have to explicitly mention who's going to be interested in this. And internal use, and interestingly, the involvement of the stakeholders, active involvement of the stakeholders in the engineering research. So that's quite different from all these, let's say, internal criteria that are only about the quality of research itself. Well, I'll skip this because I've given this example more or less already. It's about the relation between sort of things like attitude and motivation and study success. I mentioned correlation already, and a lot of studies stop at correlation because often that's the only thing you can find. But that leaves you puzzled, of course. If you see that two variables are correlated, then which is the button that you want to turn? You want to know cause and effect, of course. You want to know if I change that one, then the other one will come along. If you don't know that, then correlation doesn't say that much. So it's useful at least to know the difference. Some people already are not even aware of the fact that they're not the same. So that's number one. But number two is that I think a lot of studies should actually go for causation. You want to know what button is the, let's say, the cause button, and what button is the effect button. Why do I say all this? Well, I've already mentioned that this bridging the gap between theory and practice should be a concern for educational researchers. And fortunately it is, because recently there was a report issued by the Sector Plan Committee, chaired by Relmond, who used to be in the Delft board of the university, and I was also a member of the committee, so I knew what was going on from the inside. And some people, like Douwe, she's still there, yeah, and myself, made a plea for being very careful about this gap. And some other people denied that the gap was even there, but I think all of us felt that even if it is not there, maybe as big as some people suggest, it should really be a concern for educational researchers to try to bridge the gap between practice and research. So really increase the impact of educational research by enhancing the relation with practice and policy. Now, if you want to do that, then my suggestion is do not take natural sciences as a role model, but engineering sciences. So let's move to engineering sciences then. No, let's first go to natural sciences to show the difference. So let's first look at what are basic characteristics of natural science. And again, I'm making sweeping statements. I'm using a bit of philosophy here. In this whole lecture, you will notice that I will combine the two chairs that I have in Delft. One chair is lead for education, that's the one you mentioned. There's another affiliate chair for philosophy of technology. So I'm often trying to bridge the gap between, the gap should be there, I think, but between education and philosophy. And so I'll do a bit of both here. I'll try to combine them. So let's do a bit of philosophy of science now. What are some of the characteristics of natural sciences? Well, in the first place, they're purely descriptive. I mentioned it already. There's no normativity in the content of the knowledge. There is, of course, normativity for the knowledge. We don't take everything for granted. We have certain criteria for when something is acceptable as new natural science knowledge. But there is no normativity in the knowledge. In the laws that we state, there is no normativity. There's no law about good electrons or bad electrons. We just talk about particles that have certain behavior, and if they don't show that behavior, they're not malfunctioning electrons, they're just another particle. So they're purely descriptive. There's no opinion about reality. Natural sciences strive for maximum generalization. What they want in the end is the general theory of everything. And only then it can be written that science is dead. Well, that's probably not going to happen so easily. And there's already a book, The End of Science, written by a certain Horman many years ago. There was a lot of protest by natural sciences, of course, natural scientists. And long before that, by the end of the 19th century, there was a guy called Pauli who thought of studying physics, and it was told to him, well, don't do that because physics is dead. And that was just at the beginning of the emergence of quantum mechanics, a whole paradigm shift in natural science. So we want to go to the maximum generalization, as general as possible. We're interested in theories that describe everything that moves, or perhaps everything that has an interaction, or everything that has energy, or everything that etc. We want to go as far as possible. Context independent, that is what we want. Newton's laws hold here, on the moon, today, yesterday, in 100 years, if we're still there, they will hold everywhere, anywhere. That's the kind of laws that we're looking for in natural sciences. 99% of that is in propositions. We want it to be stated in laws, in sentences. I'll show you that engineering sciences have also other kinds of knowledge. But in natural science, everything can be written in a textbook. It's all in sentences. That is fine for natural science, and you wouldn't even want those other characteristics in natural sciences. You wouldn't like to see normativity in natural science. Like I said, it's weird for a physicist to talk about malfunctioning electrons or something. So it's weird for an astronomist to say something like it's something between a nova and a supernova. So it's a pretty good nova. That's sheer nonsense, of course. You wouldn't like to see overgeneralization. Actually, they all look alike to me. So yes, natural sciences do, of course, make distinctions. They don't talk about all the stars the same, but still, they may look the same, but they're also looking for laws that describe not this one particular star, but preferably all of them. So in that sense, the laws make them look all alike. Put opposite to that, the characteristics of engineering sciences, and really skipping all the communalities. Of course, there are communalities between natural sciences and engineering sciences. They have common criteria. Of course, in engineering sciences, we also talk about reliability and validity and all those kind of things. I just want to show the differences and show those differences that are relevant for having engineering sciences as a role model for education. A lot of engineering knowledge is not purely descriptive, but is also normative in nature. We develop knowledge about functions. We talk about the function of this and that machine. Have you ever realized that function in itself is a normative notion? It does not tell you what the artifact is actually doing. If you say the function of a car is to bring me from A to B, you can say that even if it's in the garage for repair. So it cannot even take you from A to B. But what you mean is, a car is a device that ought to enable me to get from A to B. So knowledge of functions, which is part and parcel of engineering and engineering sciences, is in itself a normative notion. It does not describe what the engine really does, it describes what it ought to do. There is an opinion about it. And if it doesn't do that, it's a broken or a malfunctioning engine. And if it does it correctly, it's a good engine, even a pretty good engine, like a pretty good supernova. No, not a pretty good supernova. So we do have an opinion about reality. Knowledge of functions, knowledge of good practice, that's part of our engineering knowledge. A lot of things that we write about is knowledge of good practice, rules of thumb. And they are not just a sort of methodological thing, no, they're really part of the knowledge that we have as engineering scientists. Rules of thumb, there's a lot of things that are part of our knowledge of rules of thumb. Knowledge of standards. They are not even the result of experimentation, they are the result of agreements. That's also a difference between engineering sciences and natural sciences. We can, of course, in the end agree about the charge of an electron, but not based on opinion. It will have to be based on hard evidence. And then you can discuss how hard that evidence is. That's what we have to agree about, but the agreement is not about the data. But what a standard is not the outcome of an experiment. That is something we discuss, and it is content of engineering sciences. We don't want to generalize as far as possible. We want limited generalization. If you are designing an aircraft, this may be a daft example, apologies, then we're not interested primarily in theories about everything that moves. We're much more interested in a theory that applies particularly to a double-decker airplane like the A380. And perhaps sometimes we want to go further, we want to have theories about all jet engines. But the further we get away from the design, the more difficult it becomes to apply that law to that particular design. So you really have to bridge an enormous gap sometimes between a general law and the practical situation. Why is that? Because to get this general law, there has been a lot of idealization. But all builders and designers of engines know that there is no ideal gas in your engine. There's real gases. And there's no frictionless situations. But in the theory, it is taken for granted that there is no friction. So you really have to bridge a gap. And the closer the theory is to the design, the happier the engineer is. So that some people sort of phrase it like this, that the engineering sciences are somewhat between those sciences that seek for general laws, that's what we call nomothetic sciences in philosophy of science, and on the other hand, the ideographic sciences that try to describe the particulars. By the way, historical sciences are the ideal of the ideographic sciences because they are really interested in the particular almost exclusively. They want to know what exactly happened there in 1600 at this little Belgian place of Newport. Who stood against each other, what happened there, who won, and etc. So that's the other end of the spectrum, you might say. So there are sciences that are really interested in the particulars only. And historians don't strive for general laws about history. They've tried for a while, but they've given up. They're much more like the storytellers now. Ask Kalinitsky, he'll confirm that. He's not really looking for very general laws about history. But natural scientists are exactly at the opposite, and engineering sciences are somewhere in between. Yes, we want to generalize away from only the A380, but not to everything that moves, but certainly not everything that has energy. I wrote an article about this, and I was inspired by an article not about engineering sciences, but about medical sciences, written by two people, Gorowitz, who was unknown to me, McIntyre is a very famous ethicist, and they wrote an article where they made a plea for medical sciences to be taken as the sciences of the particular. And the article started by saying, well, what goes wrong in a lot of medical treatments is that a doctor sees a patient as an example of a sort of paradigm patient. He has certain characteristics, so he is one of these flu patients, ignoring all the particulars of the patient. So why he has that and what are the particular characteristics that he has is all left out because medical scientists see themselves as also looking for these general laws often. And these two people made a plea and said, why not accept medical sciences as sciences of the particular rather than sciences of the universal, like the natural sciences are? And so my plea is sort of similar to that. I would like to say the same for engineering sciences. Let's accept that there are sciences that we call real sciences, genuine sciences, in spite of the fact that they are not looking for universal laws, but that they are interested in the particular. We do the same for historians, so let's do it for engineering sciences also. So not too far from the other thing design. And finally then, there's a lot of engineering knowledge that is not propositional, but is what we call knowing how, something that you cannot express in propositions. Try to explain to someone how to ride a bike, and you'll understand what is non-propositional knowledge. You can try to put it in propositions, you can write a little handbook about how to ride a bike, and you'll find out that a lot of what's in your head, the knowledge you have, cannot be phrased in words. Try to explain to someone to make a tie. As soon as I become aware of what I'm doing, I can't do it anymore. Let alone that I could express it in sentences. So there's a lot of knowledge that we have, that engineers particularly have, that is non-propositional. Like, this is taken from a book by Walter Vincenti, a very famous book about what engineers know and how to know it. He has two categories of engineering knowledge, and he calls them practical considerations, making a balance between safety and cost, material availability and the material properties. All these practical things are things that you cannot exactly express how you make that. You can try it, of course you can partially put it in sentences, but there's sort of a gut feeling that you have. That's how you do it. Same with design instrumentalities, how to tackle a design problem, how to approach it. Something that you cannot easily write in a textbook. There are textbooks written about that. But most people know that is not the full knowledge of the engineers. It's only partial. And also, sometimes we just are content with the fact that we don't know everything exactly. That it works, the outcome is okay, but we cannot exactly account for every single step in what happens. And that's what we call the miracles of technology, right? And that would certainly not be permissible in science, in natural science. But in engineering science, we sometimes do that because of this practical approach that we have, that as long as it works, it's fine. So how then do engineers work? How were engineering sciences often developed? Well, in a couple of steps. Engineers put together an artifact based on experience they have, and to the knowledge there is already past, there are some kind of outcomes of previous engineering science. So they tinker together an artifact, they examine its performance, they put the model in the wind tunnel or whatever, and then they start fiddling with variables. So they take this little airplane, make the wingspan a bit longer, and shift the center of gravity, all those kind of things, and they test for the effect on the performance. So what they investigate is the effect of the variables. So they do turn buttons, yes, absolutely. What they're interested in is the effect on performance. Does it fly better now? Does it fly more efficient? Does it fly higher? Does it fly safer? Whatever. And based on that very practical and local knowledge about this particular thing in that wind tunnel, they improve the design. And they do it again, and again, and again, until they say, well, good enough. Or money's up, or time is up, or whatever, for very practical reasons. And that's how engineering sciences were developed to a large extent, with, as a result, an improved design and some knowledge about the relation between physical and functional properties, often way from a general law about all airplanes or everything that flies or everything that moves, very local and specific knowledge, nevertheless very applicable to the next engine, to the next aircraft. In the long run, they generalize. If they collect a lot of practical experience about different sorts of aircrafts, then they get to see the bigger picture. Then they start comparing, and then they say, wait a minute, there's something common there, and then we can generalize a bit. And maybe even further than we originally thought, but usually we get stuck halfway for practical reasons, for applicability reasons. So, my plea would be, let's do it that way in education. Let's take the engineering approach and investigate in the engineering way. And how would it look like? Well, we have a term for that. We call it design-based research. It's a term that's floating around in educational design circles, and it's very much the engineering approach. So it should very much appeal to us engineers, because we recognize ourselves in it very much. How does it work? Here's a real situation with all the variables there, not laboratory-like, so the real situation, with its full complexity. Yes, with, as a result, no complete control over the total set of variables. Yes, admit it, and that will make it more difficult to get it published, because they will see it as sort of dirty research, but maybe more usable than other research. With this dual goal of having a tested intervention, like the artifact in the engineering case, and knowledge. Yes, local maybe, about this particular course, with these students, at this university, with this teacher. Yes, admit it. It's not directly about all teachers, all universities, all courses. But it gives insights that are very, very close to practice. Both descriptive and normative. The descriptive will still be there. But you will also be interested in saying, well, was it good? Was it not good? Is the outcome what we'd like to see? Can we improve? And that will usually lead to mixed methods. Because if you really want to see the inside of the process, you want to see what exactly is causing this learning effect, then very quickly you'll have to use qualitative methods also. But of course you also want some real hard evidence whether all students will be able to learn this way, and then you need quantitative data. So in a lot of educational research you will maybe begin by qualitative methods, but at a certain stage you want to go to quantitative methods also. So you'll be working with mixed method studies. Another thing that is also engineering is talking about this functioning and function. So what we do in natural sciences is we are only interested in cause-effect relations. When I do this, when I hit the billiard ball, what is the effect on the other one that it hits? It's purely cause-effect. But we are also interested in a different kind of reasoning, namely means-ends reasoning, which is logically not analogous to the cause-effect reasoning. I'm not going to explain that, it's a bit of logic, but they're not the same. And I think that often we try to look at cause-effect reasoning in education studies. And we forget that there is also this means-ends reasoning, which is also reasoning. There can also be false arguments there, so there's equally possibilities to go wrong, but it's a different kind of reasoning that has much more to do with the practical applicability. How do engineers do it then? Well, give it a shot. Try something, see if it works. It may not work immediately, so then they think, okay, what can we change? Let's see, what variables need to be changed in this situation? And so they start trying to improve, and yes, it may not work the second time either. It may not work the third time either. But every time they have the impression that, yeah, we're getting somewhere, we're getting close to the target. Sometimes you may get further away from it, because then you see that a change of variables has a negative effect on functioning, but then you quickly go back to the former situation, try something else. So that's how you try to tinker and see how you can do that. And that's a lot of how engineering sciences developed. Like, again, aerodynamics was largely developed by tinkering with airplanes in wind tunnels or other situations and trying to find out relations between the properties of the wings and the behavior of the airplane. And that is really how aerodynamics became discipline. Not by applying Newton's laws. Yes, in the end there appeared to be a relation with Newton's laws, and it matched well. But it was not bottom down. It was not top down, it was bottom up, very much. So, how about educational sciences then? Let me say again, descriptive research, modeled after natural science, will always have its value. So let's keep doing it. So, there can be a source of inspiration for interventions if you know certain laws of psychology, how people think, how people respond to all sorts of stimuli. Fine, they can be a source of inspiration. So let's keep doing that. Let's keep developing this understanding of how the human mind works, even if there's no direct applicability. Let's find it can help us find the underlying mechanisms for the relation between, let's say, the variables that we have and the functioning. Because these laws can tell us something about the underlying mechanism. So it's useful if you want to improve. But normative research should by no means seen as unscientific, unless we say now that all engineering sciences are not real sciences. I don't think you will applaud for that. Let's do the same with this type of educational science, modeled after engineering sciences. Let's accept them as real sciences. And you can see journals already shifting in the direction. There's more and more journals that see this as valid scientific studies, even though they are not modeled after the big mother natural science. So let's allow for more messy research setup, not the clean experimental or quasi-experimental research setups, where everything is nicely under control. Let's have some more messy situations. Allow for more context-specific outcomes. Yeah, limited generalizability, sure, but quite valuable if you are in a similar situation. Which, by the way, does not mean, of course, that all tinkering is acceptable, that if you just fiddle around a bit with educational interventions and you do some scrappy research with loose interviews, no, that's certainly not the case. Sometimes people suggest that, they think, this whole new forest of all these terms for qualitative research, talk about participatory action, there's all these new terms, so it's just a matter of inventing all kind of new other terms and they all feel happy, they think that if it has a name that's real research. No, of course not, that's not the case. Admitted, there is a lot of qualitative research that is just bad quantitative research. But those articles should be rejected, definitely. So it doesn't mean that suddenly everything goes. No, there's still quite strict regulations to what is a good scientific study or not. But that can be within the other paradigm. How about the role of the teacher? That was my inspiring you as engineering educators. 2 book covers, teachers are researchers, technology teachers as researchers. The right one is my favorite because I was one of the editors. And we really had a whole group of teachers in Sweden who were all involved in PhD research. So they were actually doing research in their own teaching situation. By the way, we have it in the Netherlands also, because nowadays you can get a promotion scholarship from NWO if you're a teacher, and then you can do scientific research, even totally outside teaching, so it can be real biology research, but it can also be educational research. And so we have that also. Teachers as researchers. That is perhaps the extreme. That is the most tight connection between research and practice. The teacher is his own customer, you might say. Or at least the first customer. And yes, there are some issues there. Is that a situation of independence, or is it just judging your own performance, which would not be good, of course? Well, there are ways of getting around that. There might be a possible lack of methodological expertise. If you're a teacher in some kind of subject, it may not necessarily be that you also know the methodology of social scientific research or educational research. Particularly if you're an educator as an engineer, you probably have never done any educational research. And I can tell you that's a completely different kind of research. I'm involved in the teacher education program in Delft, as Benny already said, and we always see our students go to complete culture shock. So they've done a bachelor in physics, they come with us, they have to do an educational study, and it's really culture shock. They really have difficulties understanding that people are not the same as electrons. That if you hit an electron, they will the second time do exactly the same as the first time. So they have a reliability of 0.1999, etc. And if you hit a person the second time, he may respond totally different than the first time. So you have a reliability of 0.40, and then you're quite happy. You say, well, that's an important relationship. It's significant. I still remember that I had to defend my thesis here at this university, at the Faculty of Applied Physics, and I had to explain to the professors in the committee that I was allowed to say that a correlation of 0.40 was significant in social science. And I had to write an extra appendix to the thesis to explain why in social sciences we allow for a correlation of 0.40 to be called significant. Because I still remember this professor saying to me, probably there's something wrong with your instrument, because this is way beyond what we should allow, of course. Okay, so there are issues there, yes. So there are more modest possibilities. The teacher is the problem owner, the one who brings to the fore the situation that he thinks is worthwhile, she thinks is worthwhile, interesting, because there is a problem, practical problem. Participant in the decision maker, that would be preferable, I think. Advisor in the publication process. There are numerous roles of the teacher in the whole process of educational research. I would strongly advise you to look for that role and perhaps even just take the researcher by his jacket and say, I want to have this role. Yes, there may be an issue of a possible lack of common language, because then you have to have a discussion between the educator and the researcher, and there may be issues with that, sure, yeah. But you can sort that out. If you really want to do your best, then there are ways of getting around that. And the least challenge, I think, least challenging is when the teacher just serves as the access for the researcher to respondents, including himself. And that's the typical traditional situation where the researcher would come in as an independent person and would just ask for the teacher to be used as guinea pig and the students, and that was it. That's probably still the case in much of educational research, but I think it is a very low kind of cooperation between the two. I've done something a bit naughty, perhaps. I've looked at the 20 posters that were here. I had the privilege of looking at them beforehand, and I'll share my observations with you. Now, I have to be a bit careful, because there's only one-page poster, so it doesn't describe anything in detail about the researcher. So I have to be a bit careful with this. Now, this is just an hour in the morning or so, so I'm very, very careful with this. But I think that what the maker of the poster put on the poster is probably what he thinks is most prominent. And if something is not on the poster, it is at least something that was not really at the tip of his tongue. So it says something. It doesn't say everything, it says something. So I've looked there at directly 21 posters, but one only had pictures and a little bit of text, so I really couldn't figure out what kind of research was. So nothing wrong with the poster, but it didn't have information that I needed to do this kind of analysis. Interesting. Of these 20 posters, there was only one really modeled after natural sciences. There was only one that was purely descriptive, that had no normativity in it, and perhaps there was normativity, but it was not on the poster. But again, then I think it was not at the tip of the tongue of the researcher. That probably has to do a lot with the fact that we are in engineering education here, that we already have a sort of mindset like, well, we'd like to not just describe, but do something with it. So purely descriptive studies are probably not what we see as preferable by intuition, or by our experience, let's say that way. So 19 of them really had normative notions, and they were very much sometimes even in the title of the poster, there were terms like efficiency, like effectiveness, good practice, accuracy. All those notions were all over these posters. All of the normative notions, all of them having an opinion about reality. That's the positive thing. I'm less optimistic about the number of studies that we already have that have the full-blown design-based type, as I described it, like coming up with an invention, tinkering with the variables, changing the length of the course, intensity of the course. It's still often like you design something and then you evaluate it. And I cannot see any loops in it. So you make a book and then you analyze, do the students like it, yes or no? If they like it, you leave it like that. If they don't like it, well, you start all over again or something like that. So it's only rare that you really do it the engineering way fully. Only 3 of those 20 are of that type, as far as I could read from the posters, I have to admit that. 9 out of 19 made an explicit link to theoretical theory, and therefore have what I call this, let's say, generalization ambition to a certain extent. Those are studies that really want to go beyond this individual course only. There are a lot of studies where you just assess this particular intervention, and it was good or it was not good, that's it. No link to finding out the underlying mechanism. Why did students learn something from it? Or why didn't they learn something from it? And can you derive that from a bit of psychology, a bit of educational theory? So 9 of them had explicit references to existing theories or clear ambitions to develop theoretical ideas about the underlying mechanism of what happened. 9 out of 10. I leave it to you to be happy with it, or not. But I think there is room for improvement there. And perhaps that is also because we're in engineering education, because a lot of us were educated as engineers, and probably have rather thin knowledge about educational theories anyway. There's probably something with the teacher as a researcher issue there. Because in quite some studies, there were teachers as researchers, 7. 9 had explicit teacher involvement. So as far, again, as I could read from the posters. So had active involvement. Either the teacher was the researcher himself, or in the setup of the research, there was clearly teacher involvement as a necessary element. And in the 11 other posters, there might have been teacher involvement. It was not always so clear, and of course there is always a situation where there is a teacher, so he will always, or she will always say something now and then, and the teacher overhears, the researcher overhears that, and probably picks it up and whatever, but it was unclear. It was not in the setup of the research, not explicitly at least. Again, I leave it to you to be happy with that or not, but I think there is room for improvement. So let me finalize by saying it would be good if the 3TU Centre for Engineering Education would include in its program more design-based studies. There's only 3 now out of 20, as far as I could read from a one-page poster, admitted, but I think there's room for them. That bring together research, research and teachers, educators, apologies, that make an effort to entangle development and improvement of engineering education. In many posters it was not even clear to me if there was to be a revision at all. I guess it was, but not always clear. Certainly not clear how that would be done and how it would be based on the knowledge that was gained. In which the chain effect of changes in these interventions on the performance of these interventions is studied. I think that is what we want to know in the end. What works and how does it work? How does it come that I push this button a little bit up and something happens? That's what I'm interested in, because that is what I need to be able to improve. Well, that was it. I hope it was all clear. Clearer than what's written on the blackboard here, whiteboard, whatever it is. So thank you.